Okay. I assume all of you got a note that we're recording. Sorry that I haven't started at the beginning. I'll make sure that it's automatic from now. Okay, but we got a distribution here, which is great. No freshmen this year. Here's another question that I want to get the answer to. I already have partial answer because I can see some of you. We thought about the protocol to make sure that some of you are always there, because it's easier for me to see faces. Even though you'll notice that I don't look directly at you, that's because my camera is to the side of my big terminal. But I do see the faces, and it's very helpful. I wonder what is none of the above, but someone will explain it to me later. Okay, great. So let's move on to the class. So here's an example. One of my favorite examples when we talk about why we need machine learning. This is a poem that you can read and probably understand. And this is one reason I want to see faces, because typically when I show this to people, I see some smiles. And it's hard for me now to ask questions of why you're smiling, but I guess I know why you're smiling. Because it reads very well if you try to articulate it, say it to yourself, but all of it is one big spelling mistake. And even though today we have pretty good spell checkers, your Word or Google Doc or email app, they can spell check, they can do nothing with this. It's just way too hard. And in most cases, they will not understand what's happening here. This gives you one way to think about why we need machine learning. There's no way that a conventional program, something that you will write, which is basically a set of rules, will be able to understand text like this and correct it. Everything is just too ambiguous, too variable. We need to be able to learn from experience the way you did and figure out what's wrong here and how to correct it. And this is the type of things that we're going to see throughout applications in this class. Here is another example. What we want to do here is we probably want to understand who the people are, identify people, but as I'll get to a little bit later, there's a lot more to this image that we can do beyond just recognizing that there are 3 people here and maybe who the people are. So machine learning is really everywhere. I mean, a lot of the applications that you see, from spam mail here to translation to shopping applications, are really machine learning applications. Let's just think a little bit about this spam detection. That, for example, your mail app is doing all the time, continuously trying to solve this problem. This is what we call a binary classification task. We want to assign one of 2 labels to the mail, whether it's spam or not. And classification requires that we have a model, a classifier, that determines, given this input, which label to assign. So that's what we're going to do in this class. We're going to focus on these algorithms, techniques, and representation that allow us to learn such models from data. Here is a slightly more interesting application. This is my screenshot for my mail. And the goal here is, given an email message, to categorize it and place it in a folder, one of, I don't know, 100 different folders that I have. If some of you are using folders in your mail app and you try to use the automatic classification, you see that it's pretty bad. It maybe gets it 50% of the time. Now, it's okay, it still helps, saves some time, but it's quite disappointing that something that seems relatively easy, we can still not do very well. So we need you to push machine learning forward and solve it. So what is really the problem that we're solving? In a very abstract way, you can think about it this way. You have a document. This document can be many things, but let's think about it for now as a document. And the examples that we see are document along with some label. Let's call it a color now. So I see a red document, a blue one, a green one, another blue one, yellow, and so on. And once I've seen enough examples like this, here comes a new document. And the question is, what color should this one be? What category should this fall into? And I'm going to say red in this case. That's machine learning. That's what we're going to do in this class, where we're going to try to think about different kinds of documents. Documents can be real documents, could be sentences, could be images, could be medical records. And the labels, the color here, could also be many things, from topics of documents to positive or negative, to person or location, to dogs, cats, and snakes, and so on. So that's really an abstract way of looking at what we're going to see in this class. Of course, they are the same kind of model or the same kind of framework can be used in very interesting and more involved examples. And I'm going to show some examples here today. So let's start with this example. What do you see here? What you see is a car driving in Paris, and it runs a lot of classifiers exactly of the same type that we've seen before. So essentially, all the time, it runs an car detector or image detector classifier. And if I stop it for a second, you can see what it shows. It shows a vehicle. This is the bounding box of the vehicle. And it shows a few properties of the vehicle. For example, it tries to estimate the speed, the velocity of this car, and so on. So essentially, each one of these boxes represents a classifier of the same type that I've shown before in a simple way, only that it's a larger scale model. So I'm going to run this a little bit forward. What you can see here is that it identifies some things. There are many things it does not identify, right? So on the sides above, we just passed through a tunnel. You could see many things. There are signs here. It didn't identify those. So there's a lot more things that you guys can see that the classifier here doesn't look at. I want to run a little bit faster here to get to one other point that I wanted to make. But you can see that there are also several types of bounding boxes here. They identify also pedestrian. Maybe not so well in this case. It's not exactly where the pedestrian is, but at least they try. I'm trying to get to a specific point here. Okay. Again, you can see this cyclist here. When you see the cyclist, when you drive down the road, you not only identify the cyclist, you also know what this guy might do. You kind of have a model of be careful, he might, take to the left a little bit and it's going to be dangerous. So it's not sufficient to just identify the cyclist. You also want to have a model of what might have happened, or what could happen. And that's something to keep in mind when we think about machine learning the way it is today, machine learning the way you want it to be. Let me stop this now. Of course, what you've seen here is a lot of object detections. But we've seen only one type of objects, essentially, or two types of objects. Sometimes you want to do a little bit more than that. Oh, what is this? Okay, I guess that's a mistake. So let me move to this one. That's a very interesting. So machine learning works sometimes, doesn't always work. Okay, hopefully you saw this. You're going to see it a few more times. Okay, we're going to skip forward to get to the theory. That's a good picture. Remember that. That's a machine learning mistake. So sometimes you don't care about mistakes. Sometimes you do. And why did this happen? So here is an explanation, at least an attempt and an explanation. Yeah, that's a really important point that you want to think about. How many times has the Tesla seen these kind of things? And this is really one of the challenges of machine learning in real life, that we should be able to behave even in situations that we haven't encountered millions of times before. And I gave you the example of the cyclist before. You should be able to behave also in situations where, you know, the cyclist is doing something that you haven't seen it doing before. But as people, we typically have models for this. We have expectations. Cars, not so much. But again, we don't need to work in these very complex situations. We can move back to simpler situations like this one. So you can imagine developing a person detection or even a specific people detection. And you can identify that these people are, you know, Bill Clinton, Hillary Clinton, Barack Obama. But when you look at it, you probably know a lot more things about this image. So take a look at this image again. And let me know what other things do you know given this image beyond these are the faces of 3 people. Who they are is one thing. I don't know how you know that these are presidential candidates without knowing it, but from the image, you definitely know that they are laughing. Think about what you know just from the image without background knowledge. Here is the image again. Just from the image, you know more things than just these 3 squares on the faces. Okay, you know something about the emotion. You know gender. The square on the face really has a lot more information than just there's a person here. So many of you attend to the emotion, but you can also know, for example, that there are other people in the room, right? They are probably sitting in front of people. You can see a hand there. You know that they are part of a larger party. I think you know more than just emotion. You know that probably affluent people, given the way they're dressed. Yeah, okay, they're rich. So you know a lot more people, a lot more things than just person, not person, where the face is, and potentially who this person is. And that's really important to realize that even though the way we study machine learning today, it's very, very focused. We talk about, you know, one property, one classification, one model. There's a lot more information there that we may want to attend to, and we want to think about how to get to it. Okay, so let me move on. And I want to give some examples also from natural language processing. So I'm going to give one example here. This is a few years old example from my group that hopefully you'll find interesting.
Professor, is there audio on this video? I'm not sure that we can hear.
Say it again.
Is there audio on this video? I'm not sure that we can hear it.
Or you cannot get the audio?
I don't think so on the video. Maybe someone else can confirm.
Yeah, I don't believe
we can't hear the audio.
We can't hear it.
Yeah, there's no audio.
Oh. Okay, so let me stop this. I'll check later why that is. Okay, so I'm going to move to another example then. I don't know why. So here is another interesting example from natural language processing. So some of you might have heard that there's a lot of interest these days in neural networks, very deep networks. You're going to play with some of it in the class. And specifically, one of these hot topics here is text generation or summarization. So here is a very up-to-date, this demo is a demo that was done by one of my students using state-of-the-art technology for summarization. The game here is that you're given an article. In this case, this is a New York Times article on the Beirut explosion that happened a few weeks ago. Hopefully you can read the text here. And the goal is to summarize it. Basically, in this case, we want to produce a one-sentence summarization. So you see here the top 5 summarization. So if you kind of looked at it, you saw that, Lebanon's health minister said that at least 78 people had died and 4,000 suffered injuries and so on. Now, and you know that, and fire that shook Beirut on Tuesday. When you look at the summary, I'm going to point to a few things here. Specifically, it says, the first sentence already says, the Lebanese capital, Beirut. Now notice that this is not in the original text. Somehow the summarizer knew that because it read a lot of text from before and it knew that Beirut typically appears in this context or often appears. Lebanese capital, Beirut. So it augmented the summary with information that isn't in the text. In this case, correct information, maybe we don't care. Look at the other things. At least 20 people have been killed. We know that a lot more were killed, 78 people. In this summary, more than 1,000. Wrong, of course. So sometimes the summarization hallucinates information because it really doesn't understand the text well enough, specifically doesn't understand quantities, and it doesn't understand entities well enough, so it hallucinates things. For it, 1,000 or 78 is the same thing. These are just digits. So that's, again, a very interesting failure of machine learning methods. Okay, so let's move on to another example from language. This is a story. In fact, this is a story that is taken from a reading comprehension test given to second graders. So the story is here. Following the story, there are typically a few questions that one has to answer. In this case, I rephrase the question to be statements. So the question is, are these statements true in the context of the story? But I won't ask you to answer this. I want just to see how difficult and how easy it is to understand this text. So here is one thing that we have here. We have Christopher Robin. We have Chris. His father wrote a poem. And I want to ask you the question, before we attend to many other things that are interesting in this story, I want to ask you, is Christopher Robin and Chris the same person? So while you're answering, I'm going to show you the story again, so you can look at it. And let's see. Some of you have not answered yet, so I'm going to give you time. Okay, let's look at the story again. You can always change your mind, I think. I think this is enabled. What do you think now? Okay, so people that have a view, you can open your mic and say something. Why yes, why no? Now, I realize not all of you have answered, and this is one thing that we're going to try to do in this class. We're going to try to make this participation mandatory. So all of you will answer the questions. I don't know who answers yes, I don't know who answers no. It's completely anonymous. We just know who answered. And I really would like to get all of you involved and thinking about these questions. This is rather general, but later on the questions are going to be a little bit more focused on stuff that we learn, and it's going to be important for you to kind of attend and answer. So let's see what happens now. I have 8%. At this point, I don't know how many answered, but I suspect it's not all of you. Can someone say something? Why yes, why no?
Well, I think it's yes, because in the first sentence, it refers to Christopher Robin. The second sentence doesn't indicate that the subject changed, but now the subject of the second sentence is Chris. So you'd expect that they're referring to the same person.
Okay, good. So we have an argument for yes. Anyone wants to give an argument for no?
Well, I think throughout there's, wait, can you hear me?
Yes.
Okay, so I think throughout there's kind of ambiguous, language and like, I guess, subjects that are used. So when it says Mr. Robin then wrote a book, he made up a fairy tale land where Chris lived, that kind of makes it sound like Mr. Robin and Chris could be two different people. But then also at the end, it says, people still love to read about Christopher Robin and his animal friends. And so in some parts, like I can definitely see where, he could be the same person, but then some parts, like for example, up there, where it should be like he made a fairy tale land where he himself lived or something like that. So I think like the ambiguous language kind of contributes to maybe the confusion.
What if I would ask the question, do you see my mouse?
Mm-hmm.
If I would ask the question about Mr. Robin.
So if Mr. Robin is Chris?
Yes.
I guess, yeah, because the name is Christopher Robin.
I think Mr. Robin's his dad.
a father. Yeah.
Yeah, technically, as a person who has read the books.
Yeah, because on line 4 it says his father wrote a poem, and on a line later it says Mr. Robin then wrote a book. So I think they're referring to the same person here.
So what is the answer again? Mr. Robin is the same person as Christopher Robin?
No. Mr. Robin is Chris Robin's dad.
Yeah.
I agree.
Okay. So anyhow, the goal of this exercise was to just show you that even for you, things require some thinking and maybe reasoning about it. It's non-trivial. We want programs to learn how to do it. Not easy. My final question for today on this topic is this. Here is another thing that we're going to play with in the class. This is a collection of objects. And look at it. And the question that I'm going to ask you is, what do you see? So I'm going to show you this again. Okay. Okay, I'm going to stop it now. The thing that I wanted to attend to here is mostly the fact that you answer at several different levels of abstraction. Some of you say shoes. It's true, we have shoes. Some of you say vegetables. Vegetable is a class of things, and you see there various kinds of vegetables. For example, you see onions, you see peppers. Some of you say toys. Again, it's a class of things. So you choose different level of abstraction to describe what you see there. Essentially, what you've done clustering. So there are two interesting things to point here. One is this, which is you don't necessarily name specific objects, but rather you name classes of objects, because it's very easy for you to cluster them into these classes. And the second is that it's completely trivial for you to identify this object, even though if you really look at the pixel level, some of the shoes look a lot more similar to the cars than to other shoes. And you can say this for many other things. The size doesn't matter to you, even though the size are not realistic. So the object detection capabilities are very, very good. We're going to get to this later in the class. Okay, so what are we going to do here? So we're going to deal with learning. Learning is really at the core of high-level cognition, performing what we are doing all the time, which is knowledge-intensive inferences, and from the computer science or application perspective, building adaptive intelligence systems, and in general, dealing with messy real-world data. So there are many applications and many purposes of learning that you might care about, from knowledge acquisition to integration of various knowledge sources to adaptations and decision making. Now, if I would ask you what learning is, and I'm not going to do this now, but I urge you to think about this, I'm going to use instead a definition from Herbert Simon, who's one of the inventors of artificial intelligence, a Nobel laureate in economics. He thought about learning, he defined learning to be changes in the system that are adaptive in the sense that they enable the system to do the task or tasks drawn from the same population more efficiently and more effectively the next time. And I'm going to highlight here a very, very important part of this that we're going to attend to in a very technical way in the class, drawn from the same population. Because in many respects, the way current machine learning thinks is that tasks or objects or sentences or whatever you want to deal with have to be drawn from the same population for you to be able to do something in learning, to learn from it and to use it effectively. You may want to think about if that's sufficient for you. So when you think about it, remember also the Tesla example that suddenly saw a white car upside down on the road, and it wasn't from the same population. I'm going to attend to a slightly different perspective of learning, which is the ability to perform a task in a situation which has never been encountered before. So to me, and that's the focus I'm going to put in the class, learning is really generalization. And we'll try to think about it this way and see when we can generalize, when we cannot, and what are the parameters that control this. Think about this example that I've given before, the mail application. Of course, given a new email message, I want to be able, mail, to determine whether it belongs to one category, in this case, my fall 2018 machine learning class or not, or whether it belongs to any of the other folders. And of course, it has to be able to do it, even though it has never seen this message before. So that's the challenge. And here's a question for you. This is a very difficult question, unlike the previous ones. How can we expect a program to make predictions on item it has never seen before? What should this program rely on? And of course, this is not an easy question. I still would like to see what you guys think about this. And it's most important for me that you start thinking about it. Similar training data, pattern, keywords, past experience. Past experience is correct, but it's way too general, because if you want to be able to write programs, you have to be a little bit more specific. A lot of you talk about past experience, similar features from previous examples. And next time when we start talking more concretely, starting with the badge game that hopefully all of you have looked at, we will try to make these ideas of patterns, similar features, past experience, a little bit more explicit, because the important thing that hopefully you all notice is that you have to define some things. You have to define, what does it mean features? What does it mean? How do I define my experience if you want to write a program about this? It will all boil to a representation. Learning is generalization in almost all the applications we talked about. We talked about, you know, some skills like driving and many other of the classification tasks. All of these cases, we care about the ability to perform a task in a situation which has never been encountered before. And what we'll figure out is that generalization depends on the representation. How do we represent this mail that comes into the mail app? And it really depends on the representation more than it depends on the algorithm that we use. And that's something that is going to be hopefully very, very clear as we go and try to make these things concrete in the class. Okay, so you'll think about the badges game, think about how to write a program that solves the badges game. We're going to address this next time. When we think about same population, you want to think about, again, this example versus this example. For you, it's the same population. You don't care that I change the background color. Will it affect your program? Will the program think that it's coming from the same population? Here is a nice example that I like. This is a question that I will not ask you for the answer, but I assume most of you know the answer. In New York State, the longest period of daylight occurs during the month of. Think about
June.
it for a second. Yes. Now I'm going to make one change here. Instead of New York State, I'm going to put New Zealand. Same population, different population. I just made a slight change to the text. The answer is
December.
December.
Different population.
Different population, but you want your program, if it answered the first question for the right reason, to also answer this one. So these are questions that we want to be able to think about, even not solve. This is a very hard question. Anyhow, learning is important. We all want to study machine learning. We can see it from the population, the number of people that want to take machine learning classes, and there are very good reasons for it. These are citations from some people that you want to listen to, or you may want to listen to. Machine learning is very hot, and for the right reason. And many applications that we all care about, from computer systems with new capabilities, AI, understanding human learning, understanding teaching perhaps, have to do with machine learning. And really the time is right. So we have a lot of understanding of machine learning today. We have huge amounts of online data, some annotated, some is not annotated. We're going to address this in the class and see the differences. We have a lot of computational power. This is one thing that has happened over the last few years that really contributed to the success of very, very old machine learning algorithms. And also necessity. There are many things we want to do that we cannot do by conventional programming. A lot of the examples that we've given before, you cannot program conventionally. You do need something that learns. Okay, so I want to get to the class itself, so I will not spend a lot of time here. I will just say that even though machine learning works in many, many applications, there are many things we still don't know. Many unresolved issues. And this is one reason the class is not going to be devoted to just deep neural network, which is kind of the hot thing in the last few years. But rather, we're going to spend time understanding machine learning beyond applications in ways that apply to many, many applications. Now, given that it's a very, very active field, it's difficult to decide what to teach. A lot of things, or most of the things that you see today happening, most of the papers that people publish today in machine learning will disappear and no one will know about them. I'm going to try to teach you what I think is important, really the fundamental paradigms of machine learning, some of the most important algorithmic ideas, and how to model problems using machine learning techniques. And of course, it's important, given that you're going to go out there and use machine learning and hopefully develop both applications and maybe models, what we don't know and what are the difficulties that we have to address. Here is one example that I like. Some of you may know that the US Open started yesterday. These are pictures from last year because the people on the right side of the image are not participating in this year's US Open. But here is one application that actually IBM put together, generating video highlights. And if you think about it, it's extremely difficult to look at a match and identify the highlights. You can't even imagine where to start to write a program that will identify this is a highlight or not. The key idea there was to not try to analyze the video as a way to identify highlights. Instead, they use some incidental signals, things that are correlated with the highlights. For example, noise, gasps, cheers, gestures. These are much, much easier to identify and analyze, and they're highly correlated with the highlights. Of course, there are biases because the noise when Federer plays is going to be much louder than when someone else is playing. And if it's the last point in the game, the noise is going to be louder than if it's just a mundane point in the middle. But nevertheless, with these biases, still we can use these incidental signals as a way to provide supervision. Again, a very good idea that you should think about when you think about machine learning. Okay, let's get to the class. So this is an outline of what's going to happen in the class. We're going to talk about basic problems and questions. Already next week or in the next 2 meetings, we're going to talk about a very detailed example which provides the key algorithmic idea that we're going to address many, many times in the class. We're going to talk about several paradigms, discriminative learning, generative learning, several learning protocols, and a lot of algorithms from gradient descent, which is going to be kind of one of the key tools we're going to use throughout, through decision trees, all the way to probabilistic representations and clustering. We're going to try to address modeling, evaluation, real-world challenges, and hopefully also some of the ethics of machine learning and AI. Going back to this is a slide that I showed at the beginning, just a summary. And I want to get to some other important details about the class. I'm assuming that you know this. As I said, homework 0 is going to allow you to test yourself and see whether you know it or not. We're going to assume Python. I'm glad to see that most of you have enough Python experience. We're going to start the recitations. The first 2 recitations are going to be devoted to Python. So those of you that are missing some background, please join these, ask questions. Hopefully it will help you. Yeah, this is the homework 0 that I talked about. I'm hoping to that those of you that are not comfortable with at least 2/3 of this will be brave enough to tell this to themselves, because I know that otherwise you'll just struggle with understanding what we're doing. Okay, and I always want you to participate, ask questions. It's not going to be easy, not for you, not for me. Hopefully we can do this. We'll figure out the right mechanisms, and I'm looking forward to your feedback after class for how can we do this better. One important comment that a lot of people ask about is the class is called Applied Machine Learning. Now, that means that I want to teach you machine learning, and I want us to address the applied part of machine learning. Mostly in class, we're going to mostly devote it to machine learning, understanding what is machine learning, when it works, why it works. This will involve a little bit of theory, not too deep, but most of the lectures are going to be devoted to machine learning. Most of the homeworks are going to be devoted to the apply, where we're going to ask you questions about stuff that we've done in class, but also try to get you to apply it, including teaching you things that we did not address in class, because you cannot cover everything in class. You learn also from the homework. So you will expect this split between machine learning in class, applied in the homework. That's how we design it. Of course, any feedback that you want to give, we'll listen to, and we'll try to make things such that it's clearer for you. Okay, so a little bit about the policies. We have to address cheating. That's easy. We don't want cheating. And I hope you respect that. All of you are here to learn machine learning. And I'm going to treat you as people that come to learn about machine learning, not just to take a class. Now, always, every time there are some outliers, so we're going to take it very seriously. So please respect us, respect your TAs, respect your fellow students, and take it seriously too. Okay, homework. There are going to be 5 homeworks. Collaboration is encouraged. Not easy in this situation, but I'm sure you'll figure out ways. We can help if needed. But you have to write your own solution and code yourself. This is where learning is. After you discuss this with people and you think that you figured it out, sit down by yourself and write it down. This is where you're going to learn, really. And I want you to do this. We have a late policy that is also very simple. You have credit of 4 days. That's it. So use it any way you want. Given that there are only 5 homeworks, I think 4 days credit is sufficient. Most people don't use it, but some have to use it. So just think about it and try not to use everything at the beginning. Grading, this is subject to a little bit of change, but basically that's the way it's going to look. Participation in polls is mandatory. We'll grow in time and see exactly how we're going to enforce it, but I want you to participate in at least 80% of the meetings. That means that you have to be here. I know that there are a few exceptions for people in Hawaii or Australia, but most of you are in time zones that will allow you to do this. I think it's going to make the class more interesting for you and for all of us. Project, this is for the 519 students. We're going to talk more about it as we go. Questions. In fact, I will not take questions now. I will follow the chat later. So please ask questions in the chat, ask questions in the Piazza after the class. And as I said, follow the class webpage, know the schedule and everything. Here are some details. Hopefully you know this already. And I want to finish here. And I'm going to ask you two questions. One is this. I would like you to rate the class. I'm going to try to ask these questions every time. And I'm going to ask you a more detailed question later. Now I see that many of you are responding. So we can show responses already. Oop. Okay, so in fact, I would like to have even more detailed feedback. While we are doing that, any important questions that someone wants to ask? You can open your mic.
Yeah, so homework 0, is that going to be posted on Canvas, or where do we go to get homework 0?
It's going to be on the website. Some of you cannot access Canvas yet. It will be on the website later today.
What website is that? I don't think I've seen it yet.
If you got email from me, there was a pointer to the website. If you cannot find it, go to my home page and you'll find it from the teaching link.
All right, thank you.
It was also just added to the chat.
Thanks. Any other questions? Okay, great. So with that, this is where we're going to start next time. We're going to talk about what is learning. I'm going to start by discussing the badges game. I will actually ask you to think about it, to think about the answer, of course, and to think about how would you solve it if this was your homework question. How would you write a program that solves this? And this will allow us to bring up some of the interesting questions that will come up in the class. And with that, I'm going to stop here. Thank you very much. Again, I'm not going to wait here and take questions. I'm going to expect that the chat that I can look at later and Piazza will allow you to ask questions.